And here's the result. As I said, this graphic's out of the text, but as I said, the detector really does count every ion that hits it. It says, what do you weigh? What do you weigh? What do you weigh? Click, click, click. All right? So it's really counting individual ions and fragments that hit it. And so you would get a printout like this. Now that's a bar graph. That's different from all the other forms of spectroscopy, which are a continuous line, right? This is a bar graph. And it's a bar graph because you have discrete masses that are going to be recorded. Right? You don't get 14.5, right? It's 15, 16, actually 17 as well. And let's see what else has been recorded, 13, 12, and 1. Okay? I hope those numbers kind of make sense to you, realizing that methane's what went in. Okay? Once it becomes a radical cation, things will happen to it to try to improve its stability. Now, in the case of methane, there's not much. Lose a hydrogen, right? Well, first of all, let's start with 16, because that's obvious. Right? Methane weighs 16. 1 carbon, 4 hydrogens, you got 16. So the methane that becomes a radical cation gets counted as it strikes the detector. So you see a lot of this 16 peak. And it just, the way the instrument works, it just automatically gets called the 100% peak. What peak is the tallest gets prorated to 100. The instrument's really counting. It's going to count millions and millions of ions at that mass. So it just does the math for you, calls the tallest peak 100, and all the rest are a percentage thereof, based on how many strikes actually hit the detector for those masses. Okay? Kind of makes sense? It's a really simple concept. The instrument is not easy to build. I wouldn't want to try it. But, all right. So what then is responsible for the 15 peak? Well, does it make sense that the methane radical cation might lose a hydrogen atom? Kind of makes sense, right? So it'll do that, and notice the 15 peak is pretty tall, the 15 peak is pretty tall. So losing a hydrogen atom is a relatively easy thing to do for the methane molecule. 14 would come from losing 2 hydrogen atoms. 13 comes from losing 3. 12 would be losing all of them, right? That's just the carbon. But notice how small these numbers are now. They are not so easy to do. Okay? Questions or anything like that? All right, the last peak I want to ask you about is what about this one? What about, oh, I'm sorry, it's not there. What about that 17 peak? Because notice that that's present. And I think that question's actually on the next slide. So good so far? Questions or anything? Yeah, pretty easy. When does it get tough, you ask? This is just a representation of the chemistry that's likely to happen. So there's the molecular ion losing a hydrogen atom. Now notice it's the hydrogen atom. Oh, something I should point out to you about the mass spectrometer and how it's designed to work. When those ions strike the detector, they are the ions that get counted. So there has to be a charge on the species that strikes the detector in order for the detector to see it. So in this first process where a methyl cation is released and a hydrogen atom is released, only the methyl cation is seen by the instrument. The hydrogen atom is effectively invisible. All right? It's seen by the detector. Now, realize that if the process can happen this way, it can also happen the other way. In other words, lose a hydrogen ion, not an atom. Now that changes who has the charge and who's the radical. So the hydrogen has the positive charge. The methyl now has the radical. So in that case, the hydrogen cation is seen by the instrument, but the methyl radical is not. Okay? Any process that can happen in one direction can also happen in the other direction. The difference is that typically one of those fragmentations is much more likely than the other. Okay? And it's all based on stability. It's stability of the products in one process versus the stability of the products in the other. And so the first one is a lot easier than the second one based on the data we saw on the previous slide. And then further things can happen. So the methyl cation can also lose a hydrogen atom. That's how the 12 came along, and et cetera, on down the line till you have just carbon. All right? So one thing that you might have to do from time to time with mass spectrometry is ask yourself, what kind of fragmentation process happens to be responsible for this peak? And you have to think about it a little bit. Now, one thing that should be clear to you by this first example is it's all carbocation chemistry. There's nothing new here in terms of chemistry. Remember stability of carbocations, right, from last semester? That applies to this. It's what lets you know which process is more likely to happen. And as with IR, when you're looking at a real mass spec, you cannot try to find meaning to every single peak that's present. You find meaning to the couple of peaks that are important in the context of a particular question. Okay? And I hope you realize that's the message throughout this spectroscopy chapter, actually chapters, because the next one's NMR. NMR is the one that you can be most thorough with. You can find meaning to just about everything. All right. So they are fragmentation reactions. And some of these statements are written versions of what I pretty much just said. So we do refer to them, the number, as mass to charge ratio. The charge for you guys is always going to be 1. So the mass to charge ratio will equal the mass of the ion. As I said, only ions appear, neutral molecules and radicals in the data set that comes out of a mass spectrometer. Individual, and that's an important issue, individual detected. This is the one that we talk about where individual molecules, ions, etc. are actually seen. Everything else, it's the ensemble. It's the mixture. It's a lot of molecules that are seen by the instrument. Okay. Yes, we do have different techniques within the context of mass spectrometry. What I'm discussing with you right now is referred to as electron impact. That's the EI, mass spectrometry, I should say. There are other forms. There's chemical ionization. There's a bunch of other forms that keep popping up. Most of those occur because of biochemistry these days, because you're dealing with huge molecules. And so extra techniques had to be developed for mass spectrometry in order to process the data that comes out of those huge molecules. All right.